Number 22, generate parentheses. Given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. I guess a question that I could ask might be, is it always these parentheses? As in like all the other ones are called something else like brackets or angle brackets. So only these are called or considered parentheses. And is it always going to have like complete pairs? Because I remember doing a problem where we had to figure out like a Boolean output if there were like incomplete pairs. But reading this again, when they say well-formed parentheses, seems to suggest that no, there may be instances where that may not be true. Looking at the examples, example 1, input is 3, so we have 1, 2, 3, 4, and 5 different ways to express that. And example 2, where n is 1. Since there's only one pair, there's only one combination of well-formed parentheses, which is just open and close. So I'm guessing this is considered the edge case. Not sure what other edge case there could be, seeing from the constraints here, starting at 1 as a minimum, but also looking at the maximum of 8, curious what that number looks like, because 1 is 1, 3 was 5. I don't know the mathematics of like how quickly this combination will multiply. Another thing that I'm seeing here is that we have an interface of a list. I guess we will be putting our generated parenthesis combinations inside the list. I can't think of anything else that should be covered under the examples and edge cases. So now we are on the approach stage of Reacto, and I was just trying to remember the old problem that I had to solve for the Boolean output of whether the parentheses were formed properly or not. And that sort of used stack, I think. So some form of recursion. I think our teacher also mentioned dynamic programming. Not sure how that would look. I didn't consider that angle whatsoever. But I think a good way for us to kind of get a hint of what this might cover is looking at the topics. But I'm curious. So it's a very, very popular question, it seems. Topics, dynamic programming, backtracking, and string. So I guess we should definitely try to use dynamic programming. I'm not sure if I have used backtracking in any of my approaches so far. I've heard that this is a very prominent approach when it comes to a lot of the Leetcode problems. Also, the acceptance rate is very high, it seems. A lot higher than even the easy problems, which is interesting. So let me think. I have no idea what entails backtracking, like tracking backwards, some form of reverse engineering type of idea. But I don't quite grasp what that looks like. Knowing that there may be some sort of recursion and dynamic programming and string, I'm guessing that as a medium problem of all things, which I think might be the first one on the channel, I want to say that there's gotta be like a string builder as part of the solution. And from what I recall from my climbing stairs problem, this is going to involve the, dp whatever is dp of n minus 1 plus dp n minus 2. But that was like the most basic problem. Not 100% sure if that sort of formula applies broadly to any dynamic programming problems. I think the best place to start is looking up what the heck backtracking really is. So it's a problem-solving algorithmic technique that builds solutions incrementally and abandons a path, which is referred to as backtracking, as soon as it determines that the path cannot lead to a valid solution. Sounds like a very wise algorithm that could be applied to real life. If only people could do this, sounds like an amazing way to live your life. It is commonly used for constraint satisfaction problems like Sudoku, mazes, and the N-Queens puzzle. I don't know what N-Queens puzzle is. How it works: the algorithm explores a tree of possibilities using DFS approach. It makes a choice, moves deeper, and checks if the choice violates any rules. So you choose first, make a decision that moves you closer to a potential solution, and then you check the constraint. If it breaks it, then you back off, and then ditch that branch, and then try the next available option. Common application. Backtracking is ideal for problems where you must test multiple combinations, permutations, or subsets, which is why I guess it goes hand in hand with our dynamic programming type of questions. The advantage is that it is far more efficient than brute force enumeration because it prunes invalid paths early. Okay, it uses less memory than storing all possible answers, since it only retains the current branch in memory. I remember during the stairs problem, one of the ways in which the optimal solution optimized the space complexity was by ditching just entirely not worrying about storing the previous DPs, but instead just focusing on the two variables needed to compare. So I'm wondering if that is also applicable here. Cons: because it involves an exhaustive search through a decision tree, the time complexity can be exponential in the worst case scenario. Sounds like a very reasonable thing that happens in real life as well. So on another note, I decided to look up backtracking's difference with dynamic program. And as I was reading through this, one of the things that they pointed out, at least when you're doing Leetcode and the constraints, is if n is less than or equal to 20, then the exponential nature of backtracking is acceptable. But if n is greater than or equal to 10 to the third power, then you start needing dynamic programming or a greedy approach. But also here it mentions that if the function asks for a list of lists, use backtracking. If it asks for an integer representing a count or extreme value, use dynamic programming. I got to the solution with the help of AI, but I'm gonna try to go over the steps that I followed to get here. One of the first things I wanted to do was make a list called results because we needed to return results which would have all of our combinations in them. And then I was guided that we need to come up with a helper method, as they like to call it, called backtrack. Originally, I thought that backtrack and dynamic programming was used in conjunction. Apparently, it's not after my research. So I made the backtrack function, which takes in couple parameters, so our results, and then the current, and the open and the close, and the end, which is what we were given initially. Base case is quite important because that's when we know we are done with our work here. And here it says if the open and the close are the same, that's when we know we're done here. Looking at these two if statements now, the first one is basically saying that we still have open parentheses left that we need to place, so we're going to add one here. The second one is saying that we have more open parentheses than the closed ones. So that means that there is a mismatch in the number of parentheses open and close. So aka we have to close some more. So we are going to put a closing parentheses right here. I think a good way to test the understandings is kind of running through the example that they gave us, which is n equals 3. So we start with basically open, an empty string. And because open, which starts at 0, is less than 3, we kind of add a bunch of opens, and then we get to open equals 3. And because open is equal to 3 now, we have to move on to the next part. It's not equal, it's not less than, so we have it right here where we have to start worrying about the closing parenthesis, and so start adding the closing parentheses. So we have explored this path, and after that, this part was a little tricky for me. We don't subtract 1 out of the open. We just go back to the last instance that was not explored. So because we have explored this path of, okay, we have 3 open parentheses, and then we close all 3, and that's what happened. Before we get there, what do we have? We have 2 open that is yet to be explored. So then we kind of close it and then try to open it and then make a new combination and reach this particular solution or result, and then we go back again and try some other combination and then add it. Finally, we go to the last possible combination that looks like this. Even looking at the solution, especially following through with the example, I think is a little bit confusing, but that is the first stab at our medium problem with the crutches of having our Claude. Okay, so we did our backtracking, which is explained right here. Time complexity is O of 4n over square root of n. There's no way I would have known this time complexity, honestly. It's like foreign language right now. I don't know where those numbers are coming from. This guy's lonely here. Yeah, I'm not sure if I understand all of it, but I think we start with exposing these problems. So if I were to revisit this problem in a few days and had like 0 memory whatsoever, I feel like I would remember making a list that we have to return. That part is clear. The fact that I have to use backtracking will be memorable, but then building this function result I get, and then we have open and close and current, and like it all makes sense. It's just like kind of chunky, and then this part makes sense, complete sense. That's the base case. But yeah, I think we're gonna need to repeat this section a little bit to better understand. Like the code itself is very simple, but then what it's saying to me feels foreign still. That was the problem for today. Thanks for watching and hope you guys are learning as well. Take care. Bye.